Hello everyone. In today's lecture, we are going to discuss about JK flip-flop. In continuation with the discussion on flip-flops, we have discussed earlier about SR flip-flops and D flip-flop. Today we are going to discuss about JK flip-flop. SR flip-flop is set and reset. D is data or delay flip-flop. And JK, it was named after the inventor Jack Kilby. Jack Kilby flip-flop. It is also known as JK flip-flop. This flip-flop serves the purpose of storing and manipulating binary information within the digital systems. It is an improved version of SR flip-flop. And as we discussed above, the flip-flops has the common applications. It can be used in counters, shift registers, memory units, frequency division, digital clocks. All these things apply flip-flops. So this is the symbol of JK flip-flop. When we see a JK flip-flop, it has two inputs J and K, and it has a clock, and then two outputs are also there. So this is the circuit diagram of JK flip-flop with NAND gate. So if you see here, the same circuit here is an SR latch is there here, and the two NAND gates are there. The same number of gates, almost the same connections, right? Except one thing, that is, for these first two NAND gates, we have three inputs rather than two inputs in the case of SR flip-flop. So SR flip-flop has a drawback. So if you have noticed, when we realize either using NAND gate or NOR gate, when S is equal to 0 and R is equal to 0, or S is equal to 1 and R is equal to 1, in two different cases, we have the invalid states or undefined states, right? That is, Q as well as Q bar will be either 0 or will be equal to 1, which is not acceptable. So see, the state 0, 0 and 1, 1 was unused in either one of them, right? Is unused as in the SR flip-flop when it has been realized with NAND and NOR respectively. So this drawback, so one state is being wasted. So this drawback is being overcome by SR flip-flop, JK flip-flop. So if you see the JK flip-flop, the one difference when compared to SR flip-flop and JK flip-flop is Q dash is being given as input to this NAND gate, and Q is being given as input to this NAND gate, right? So see here, Q dash, normally if it is an SR, we'll be having these two inputs, clock S and here clock R, right? Here we have one more input, which is a feedback taken from Q dash and given to J, this NAND gate, and Q, which is being given to K. This is the modification what is done in order to overcome the problem of SR flip-flop. But even then, in JK flip-flop, in these conditions, when S is equal to 1 and R is equal, J equal to 1 and R is equal to 1. If you see, a raise around condition will appear. Right? We have different techniques to overcome that, but even then that state could be reused. So the drawback of SR flip-flop is overcome in the case of JK flip-flop. This is the truth table of SR flip-flop. JK flip-flop. So when the clock is 0, irrespective of whatever be the input is, it retains the previous state. So when J and K are 0, as irrespective of the present state, right? The next state will be the same. That is, if present state is 0, next state also will be 0. If present state is 1, next state also will be 1. We can actually we'll be doing this with the help of circuit. When I give 0 and 0, is considering Q is equal to 0 and Q dash is equal to 1. So this input will be going here 1, and here J is 0 and clock means it is 1. So 101. Similarly, here also we'll get a set of ones. We know the truth table for NAND gate. When it has been given to the NAND gate, we'll get a certain set of outputs, and that is what is mentioned here. Now, when two different other inputs are being given, 0, 1, and two different possibilities of present states, 0 and 1. So the output is 0. So next state always will be 0. And in the case of j is equal to 1 and k is equal to 0, and whatever be the present state is, the next state will be 1. So the next state is equal to 1. And the last case is when j and k are is equal to 1, right? What happens is it is the inverted version. That is, if present state is 0, next state will be 1. If present state is 1, next state will be 0. So we have written as qn dash, that is present state's complement. Now comes the characteristic table. As we know, the characteristic tables is the inputs and the present state versus the output. So which we'll be deriving it from the truth table. So this is the characteristic table. From the characteristic table, we'll be drawing the excitation table as we have discussed in SR flip-flop. Then we'll be drawing finding the characteristic equation in order to draw the logical circuit. So characteristic equation is derived by drawing a K-map for the characteristic table. So this is the characteristic equation or output equation of a JK flip-flop. And so this is for your assessment. The output Qn of a JK flip-flop is 0. It changes to 1 when a clock pulse is applied. The input Jn and Kn are respectively 1 and 0, or you can go through this. When both the inputs of JK flip-flop cycles are high, the output will be, right? What will happen? Will it toggle or will there be no change? So this is for your study, and thank you.